The bolt slams forward for the 473rd time in 60 seconds. Staff Sergeant Michael Kovalchik watches through the observation port as his modified .30 caliber machine gun chews through another belt, the cyclic rate visibly faster than the weapon sitting on the adjacent test stand. It's March 9th, 1944, and what Kovalchik has done in the armory shop at Camp Butner, North Carolina, is technically a courts-martial offense. He's altered the breech mechanism of a standard-issue M1919 Browning, without authorization, without engineering oversight, and without any formal training in weapons design. The timing device clicks to a stop. 803 rounds per minute. Kovalchik feels his stomach tighten. The standard M1919 fires between 450 and 550 rounds per minute. He's just increased the cyclic rate by 60%, using nothing more than a file, a set of calipers, and an understanding of mechanical timing that came from 3 years working on railroad locomotives in Pittsburgh. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Lieutenant Colonel Andrew Hartman stands beside him, arms crossed, face unreadable. Hartman commands the 3rd Armored Division's Maintenance Battalion, and he's watching a 26-year-old armorer demonstrate something that Springfield Armory's engineers have declared mechanically impossible. The gun that shouldn't work has just fired 1,200 consecutive rounds without stoppage, malfunction, or visible stress to any component. "Sergeant," Hartman says slowly, "do you understand what you've done?" Kovalchik knows exactly what he's done. He's modified the breech block's locking surfaces by removing 0.04 inches of material from the cam track, altered the barrel extension's engagement timing by reshaping the locking lugs, and adjusted the recoil spring tension to compensate for the faster cycling speed. Each modification violates direct orders from Ordnance Department Technical Manual 9-1-1919 that explicitly states, "No alterations to breech mechanism, dimensions, or timing are authorized under any circumstances." But Kovalchik also knows what he's seen. He knows about the casualty reports from Tunisia, where German MG-42s firing 1,200 rounds per minute shredded American infantry before Brownings could generate effective suppressive fire. He knows about the after-action reports from Kasserine Pass, documenting how Wehrmacht machine gunners sustained fire density that American weapons couldn't match. And he knows that official channels have spent 18 months studying the problem while soldiers died because their guns fired too slowly. The question hanging in the testing bay isn't whether Kovalchik broke regulations, it's whether his illegal modification will save American lives or end his military career. Possibly both. The institutional resistance to breech modification wasn't arbitrary. It was rooted in 70 years of firearms engineering consensus that treated the breech mechanism as the most critical and delicate component in any automatic weapon. The breech was where controlled explosion met mechanical precision, where chamber pressure measuring 35,000 pounds per square inch had to be safely contained while simultaneously driving the gun's operating cycle. Any miscalculation in breech timing, any error in locking surface engagement, could transform a machine gun into a fragmentation grenade. Springfield Armory, America's primary weapons development facility since 1794, had established design protocols that governed breech mechanism specifications with religious precision. The M1919, Browning's breech block, weighed exactly 2 pounds, 11 ounces. Its locking surfaces engaged the barrel extension through a cam track machined to tolerances of plus or minus 0.005 inches. The timing from the moment the cartridge fully seated in the chamber to the instant the firing pin struck the primer was regulated to within 0.003 seconds. These weren't arbitrary numbers. They represented the accumulated wisdom of generations of weapons designers who'd learned through catastrophic testing failures that breech mechanisms demanded conservative engineering. Push the timing too fast and the breech might unlock while chamber pressure remained dangerously high, causing casehead separation and potentially destroying the weapon. Make the locking surfaces too shallow, and the breech might fail to lock completely, allowing gases to escape rearward into the gunner's face. The technical literature was filled with cautionary examples. In 1897, A French Hotchkiss prototype had exploded during trials at Bourges Arsenal, killing 2 engineers because the breech unlocking cam had been machined 0.01 inches too shallow. In 1908, a German Maxim variant had suffered catastrophic bolt failure at Spandau, proving grounds after designers attempted to increase cyclic rate by reducing breech lock time. The bolt had shattered into 17 pieces, sending shrapnel through the gunner's protective screen. By 1940, institutional memory of these failures had calcified into absolute doctrine. Ordnance Department regulations stated explicitly that breech mechanism modifications required formal approval from the Chief of Ordnance, comprehensive metallurgical analysis of all affected components, and minimum 6-month testing protocols before field implementation. The regulations existed for sound reasons, but they also created a system where innovation moved at bureaucratic speed while combat moved at the speed of incoming fire. Michael Kovalchik had learned mechanical timing not in ordnance schools, but in the Pennsylvania Railroad's Altoona maintenance shops, where his father had worked for 32 years. Between 1936 and 1941, before the draft notice arrived, Kovalchik had spent 6 days a week maintaining K4 class Pacific locomotives, massive steam engines whose valve timing and reciprocating components operated on principles that weren't so different from automatic weapons. A locomotive's valve gear controlled when steam entered and exited the cylinders, determining how efficiently the engine converted pressure into motion. Get the timing wrong by even a fraction of a second, and the locomotive either wasted fuel through inefficient steam usage or risked mechanical damage from excessive pressure remaining in the cylinders during the compression stroke. Kovalchik had learned to read timing by sound, by vibration, by the subtle changes in how components moved under load. He'd learned that timing wasn't just about following specifications. It was about understanding the relationship between force, motion, and material strength. A cam track that seemed perfectly adequate at slow speeds might bind or gall under rapid cycling. A spring that provided sufficient force for standard operation might cause excessive battering if the cycle rate increased. These were lessons learned through observation and experimentation, through watching what worked and what failed when theory met mechanical reality. When Kovalchik arrived at Camp Butner in February 1943, he was assigned to the 3rd Armored Division's Armory section as a small arms repairman, technical grade 5. The assignment was routine: fix damaged weapons, maintain inventory, ensure that every M1919 and M2 Browning met specifications before issue to combat units. It was supposed to be a rear echelon job, the kind of position that kept you away from actual fighting. But Camp Butner, in 1943, wasn't a quiet maintenance depot. It was a combat training facility where tank crews and infantry practiced coordinated assault tactics before shipping to North Africa and Europe. Kovalchik watched exercises where American machine gunners tried to provide suppressive fire against simulated German positions. He watched them fire their 450 rounds per minute Brownings, while instructors playing the role of Wehrmacht gunners demonstrated the sustained fire density that MG-42s could generate. The disparity was obvious and troubling. German cyclic rate advantage meant that in any firefight, Wehrmacht gunners could put nearly 3 times as many rounds downrange in the same time period. That density of fire didn't just kill more effectively. It suppressed movement, pinned down advancing troops, and created psychological pressure that turned brave soldiers cautious. American infantry doctrine called for machine gunners to provide covering fire while rifle squads maneuvered. But if the covering fire was too light to keep enemy heads down, the doctrine collapsed into casualties. After-action reports from Tunisia confirmed what Kovalchik saw in training. The reports arrived at Camp Butner throughout spring and summer of 1943 as divisions that had trained there shipped overseas and encountered actual combat. The language was carefully clinical, but the implications were stark. Enemy automatic weapons demonstrate superior suppressive capability due to higher cyclic rate, one report from the 1st Infantry Division noted. Recommend investigation of methods to increase M1919 fire density to competitive levels. Another report from the 9th Infantry Division was more direct. German MG42 effective rate of fire creates disproportionate casualties during assault phase. American machine gun sections, unable to provide equivalent suppressive effect. Request priority development of higher rate of fire weapons. Kovalchik read these reports in the Armory's technical library, where training, bulletins and field manuals were supposed to keep rear echelon personnel informed about frontline developments. The reports disturbed him because they described a problem he understood mechanically. The Browning wasn't firing slowly because of weak springs or insufficient gas pressure. It was firing slowly because its breech timing had been designed for reliability and longevity, not maximum cyclic rate. The M1919 used what John Moses Browning had called hesitation lock, a timing system where the breech block locked into battery for a brief moment after chambering the round, ensuring that the cartridge was fully seated and the firing pin wouldn't strike until the chamber was completely sealed. That hesitation, measuring roughly 0.015 seconds, was a safety feature that prevented out-of-battery detonations. It was also the limiting factor in cyclic rate. Kovalchik began studying the M1919's technical drawings during evening hours when the armory shop was empty. The drawings were available to any qualified armorer, filed in massive blueprint cabinets that held specifications for every weapon the Army issued. He spread the breech mechanism drawings across his workbench and traced the cam track that controlled breech lock timing with his finger, measuring angles with a protractor, calculating the relationship between breech travel distance and time. The cam track was a precisely machined groove in the breech block that engaged a stud on the barrel extension. As the barrel and breech recoiled together after firing, the cam track rode along the stud, gradually rotating the breech block until the locking lugs disengaged from the barrel extension. The shape of that cam track determined how quickly unlocking occurred. A steep angle meant faster unlocking. A shallow angle meant slower, more gradual disengagement. Browning had designed the cam track with conservative angles that ensured the breech remained locked until chamber pressure had dropped to safe levels. That conservatism was admirable engineering for commercial and military weapons that needed to function safely in inexperienced hands. But Kovalchik thought it might also represent over-engineering for professional military use, where trained gunners maintained their weapons meticulously and ammunition quality was controlled. The insight came during a night shift in October 1943, when Kovalchik was repairing a damaged M1919 that had been run over by a tank during training exercises. The barrel extension had been bent, requiring replacement, and as he removed the damaged component, he noticed something about how the locking lugs engaged the breech block. The engagement was deep, more than seemed necessary for the brief moment of lock. He measured the engagement depth, 0.375 inches. Then he consulted his worn copy of Hatcher's notebook, the unofficial firearms engineering Bible written by Major General Julian Hatcher, a legendary ordnance officer who'd spent 40 years studying automatic weapons design. Hatcher's calculations suggested that safe breech locking for .30 caliber ammunition required minimum engagement depth of 0.25 inches at the moment of cartridge detonation, 0.375 inches versus 0.25 inches. That was a safety margin of 50%, far more than most mechanical systems employed. Kovalchik understood safety margins. Locomotives used them extensively. A valve that could theoretically handle 200 pounds of steam pressure was rated for 150 pounds, providing a 33% safety margin against unexpected pressure spikes. But locomotive builders didn't use 50% margins because excessive conservatism wasted efficiency. A valve that could handle 200 pounds shouldn't be limited to 100 pounds unless there were specific reasons to expect dangerous pressure fluctuations. The .30 caliber cartridge had been standardized in 1906. Nearly 40 years of manufacturing had eliminated the quality variations that might justify such enormous safety margins. What if Browning's breech timing wasn't optimized for modern ammunition manufacturing? What if the hesitation lock that ensured safety with early 20th century cartridges was no longer necessary with 1940s quality control? The questions felt dangerous because they challenged the wisdom of John Moses Browning, America's greatest gun designer, a man whose firearms genius was considered beyond question. But Kovalchik had learned on the railroad that no designer, however brilliant, could predict future manufacturing improvements. Browning had designed the M1919 in 1919 when ammunition quality varied significantly between manufacturers. By 1943, military cartridges were produced to specifications so tight that pressure variations measured less than 3% across entire production lots. The theoretical answer was obvious. If ammunition pressure was consistent and predictable, breech lock duration could be safely reduced without increasing risk of out-of-battery detonation or casehead separation. Reducing lock duration would increase cyclic rate because less time spent locked meant more time available for the full operating cycle. The practical answer was more complicated. Theory was cheap. Proving theory required testing that violated regulations, risked destroying government property, and could end a military career if the experiment failed catastrophically. Kovalchik was an enlisted man with no formal engineering credentials, no authority to modify weapons specifications, and no institutional protection if something went wrong. He thought about the after-action reports describing American soldiers pinned down by MG-42 fire. He thought about his father's advice delivered during his last visit home before shipping to Camp Butner. If you see something wrong and you can fix it, you fix it. You don't wait for permission. You fix it and accept the consequences. In November 1943, working alone in the armory shop during night shifts, Michael Kovalchik began illegally modifying a reject M1919 that had failed proof testing due to a hairline crack in the receiver. The gun was scheduled for demilitarization and scrap, which meant nobody would miss it if his experiment destroyed it completely. He rationalized that he wasn't really violating regulations because he was modifying a gun that had already been rejected for service. The rationalization was thin, but it was enough. His first modification was conservative, almost timid. He removed 0.015 inches from the cam track's engagement surface using a fine file and constant measurement with calipers. The work took 4 hours of careful, material removal, checking and rechecking dimensions to ensure he didn't remove too much. 0.015 inches was roughly the thickness of 4 sheets of paper. One mistake and he'd have to start over with a different breech block. When he'd finished, the cam track looked almost identical to the original. The change was invisible to casual inspection, but mechanically, that tiny material removal meant the breech would unlock 0.007 seconds faster on each cycle. It didn't sound like much, but in a weapon firing 500 times per minute, those fractions of seconds accumulated to dozens of additional rounds. He assembled the gun on November 23, 1943, mounting it on the armory's test stand typically used for headspace and timing checks. The test stand wasn't designed for sustained fire testing, but it would contain any catastrophic failure. He loaded a 50-round belt of ammunition, stepped behind the protective shield, and pressed the trigger. The gun fired. The sound was slightly different, sharper, the rhythm faster than a standard M1919. He counted instinctively, measuring time against the familiar rate of fire he'd heard thousands of times during maintenance testing. Faster. Definitely faster. When the belt ran empty, he examined the weapon carefully. No cracks, no unusual wear patterns, no signs of excessive stress on the breech block or barrel extension. The spent casings looked normal, no casehead separation, no excessive pressure signs. The gun had fired 50 rounds at an elevated cyclic rate without mechanical failure. He measured the cyclic rate using a stopwatch and careful counting during subsequent tests, 540 rounds per minute. He'd increased the rate by 18%, with a modification so small that it required magnification to see. The result was promising, but insufficient. 540 rounds per minute was better than 450, but it still didn't match the MG-42's 1,200 rounds per minute. Over the next 3 months, Kovalchik continued his unauthorized experiments. Each modification pushed the boundaries slightly further. He removed 0.02 inches from the locking lug engagement surfaces, reducing the depth of lock. He reshaped the cam track to steepen the unlock angle by 3 degrees. He adjusted the recoil spring tension to compensate for the faster cycling speed. Each change was documented in a private notebook he kept hidden in his footlocker, complete with measurements, calculations, and test results. By February 1944, his modified gun was firing 680 rounds per minute, a 50% increase over standard M1919 specifications. The gun remained mechanically sound, with no signs of accelerated wear or dangerous stress, but Kovalchik had reached the limit of what he could safely test alone in the armory shop. Further modifications would require sustained fire testing under realistic conditions, thousands of rounds across hours of continuous operation to prove the gun wouldn't fail catastrophically during actual combat use. He needed official support, which meant revealing what he'd done. The decision kept him awake through several nights as he weighed the risks: courts-martial for unauthorized weapon modification, destruction of a military career, potential criminal charges if anyone decided he'd sabotaged military equipment. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Against those risks sat the knowledge that soldiers were dying because their machine guns fired too slowly. The choice wasn't really a choice at all. Lieutenant Colonel Hartman listened to Kovalchik's explanation for 47 minutes without interrupting. The meeting took place in Hartman's office on March 10, 1944, less than 24 hours after the demonstration that had produced 803 rounds per minute. Kovalchik had brought his notebook, the one he'd kept hidden for 4 months, containing every measurement, calculation, and test result from his unauthorized modifications. Hartman was 51 years old, a career officer who'd served in the punitive expedition against Pancho Villa in 1916 and commanded a machine gun company in the Meuse-Argonne offensive in 1918. He understood automatic weapons from the perspective of someone who'd watched men die when guns jammed at critical moments. He also understood military regulations and the institutional fury that would descend if word spread that an enlisted armorer had been modifying weapons without authorization. "You realize," Hartman said when Kovalchik finished, "that what you've described is approximately 47 violations of Army regulations, unauthorized modification of military property, conducting unsupervised weapons testing, using reject firearms for experimentation, failure to report non-standard procedures through proper channels. I could have you court-martialed and you'd spend the rest of the war in Leavenworth." "Yes, sir." "You also realize that if your modifications caused a weapon to explode in combat, killing American soldiers, you'd be personally responsible for those deaths?" "Yes, sir." Hartman opened Kovalchik's notebook and studied the entries. The handwriting was meticulous, the measurements recorded with precision that matched anything Springfield Armory's engineers might produce. The calculations showed understanding of breech timing, chamber pressure, and mechanical stress that went beyond what the Army taught in armorer schools. This wasn't amateur tinkering. This was competent engineering applied by someone who'd learned mechanical principles outside traditional weapons development channels. "Your father worked for Pennsylvania Railroad," Hartman said, reading from Kovalchik's service record that lay open on his desk. "Yes, sir. 32 years in the Altoona shops. Valve timing on locomotives. That's where you learned this?" "Yes, sir." "The principles are similar. You're controlling when components move relative to each other, making sure forces don't exceed what the materials can handle, optimizing the cycle for efficiency." Hartman closed the notebook. "I'm going to ask you a direct question, Sergeant, and I want an honest answer. Do you believe these modifications are safe for combat use?" Kovalchik met his eyes. "Sir, I've fired 1,200 rounds through that gun over 3 months. I've tested it cold, hot, dirty, and clean. I've pushed it harder than any gunner would in actual combat. It hasn't shown any signs of stress fractures, excessive wear, or timing problems. The breech locks properly on every cycle. Ejection is positive. The gun runs smoother at 800 rounds per minute than most. M1919s run at 450. That's not what I asked. I asked if you believe it's safe." "Sir, I believe it's safer than sending soldiers into combat with guns that fire half as fast as what they're facing. The MG-42 kills Americans because our gunners can't generate enough fire density to suppress German positions. Every after-action report from North Africa says the same thing. We're outgunned because we're shooting too slowly. Hartman stood and walked to his window, overlooking the training ranges where tank crews were running qualification courses. He was silent for nearly a minute. When he spoke, his voice was careful, measured. If I forward this to Ordnance Command through official channels, they'll bury it. Springfield Armory has spent 18 months trying to develop a higher rate of fire, 30 caliber. They've concluded it's mechanically impossible without a complete redesign. An enlisted armorer claiming he solved the problem with a file will be dismissed as either lying or dangerously incompetent. Yes, sir. But if I don't forward it, and it actually works, soldiers die who didn't have to die. Yes, sir. Hartman turned from the window. We're going to conduct formal testing, sustained fire, environmental stress, everything Springfield Armory would do if they took this seriously. We're going to document every round fired, every temperature variation, every component inspection, and we're going to do it quietly because if word reaches Ordnance Command before we have irrefutable data, they'll shut us down and court-martial both of us. Over the next 6 weeks, Kovalchik's modified M1919 underwent testing that would have satisfied the most rigorous ordnance protocols. Hartman brought in Master Sergeant Frank Delacroix, the division's senior small arms instructor, who'd spent 19 years teaching machine gunnery and knew the M1919 better than most engineers at Springfield Armory. Delacroix was, skeptical initially, convinced that any significant cyclic rate increase would cause catastrophic failure. The first sustained fire test happened on March 15th on Camp Butner's long-range qualification course. They mounted the gun on a standard M2 tripod and loaded 2,000 rounds of belted ammunition. Delacroix handled the gun personally, wanting to feel any abnormalities in vibration, recoil impulse, or mechanical timing that might indicate dangerous stress. He fired in controlled bursts, 50 rounds, pause, 50 rounds, pause, maintaining the discipline that prevented barrel overheating. The gun's sound was noticeably different from standard M1919s. Sharper, more continuous, the individual shots blending into a sustained roar that sounded almost like tearing fabric. After 400 rounds, Delacroix stopped and examined the weapon carefully. "Barrels heating faster," he said. "Not dangerous, but noticeable. The higher cyclic rate means more rounds, through the barrel in the same time period, so more heat generation. We'll need to watch this during extended firing," he continued. 600 rounds, 800, 1,000. The barrel was glowing visibly now, heat waves rising from the metal. Standard doctrine called for barrel changes every 200 rounds during sustained fire to prevent overheating damage. The modified gun was running hotter than standard specifications suggested was safe. At 1,200 rounds, Delacroix stopped and signaled for a barrel change. They'd brought a spare barrel heated to the same temperature as the gun barrel in a field oven, standard practice for preventing thermal shock during barrel changes. Kovalchik performed the change in 43 seconds, well within the acceptable time standard. They continued firing, 1,500 rounds, 1,800, 2,000. When the ammunition was exhausted, they disassembled the gun completely for detailed inspection. Kovalchik laid out every component on a clean tarp, while Delacroix examined each part with calipers, magnifying glass, and experienced eyes that had seen what metal fatigue looked like before it caused catastrophic failure. "Breech block shows normal wear patterns," Delacroix said, measuring the locking lugs with calipers. "No unusual erosion, no cracking, no signs of excessive battering. Barrel extension looks good. Firing pin, extractor, ejector, all within acceptable wear limits." He set down his tools and looked at Kovalchik. "This shouldn't work. Everything I know about machine gun design says that reducing breech lock engagement should cause timing problems and increase failure rates. But I just fired 2,000 rounds at 800 per minute, and the gun ran flawlessly." "The breech doesn't care how long it's locked," Kovalchik explained. "It cares that it's fully locked before the cartridge fires, and that chamber pressure has dropped to safe levels before it unlocks. Modern ammunition is so consistent that we can safely reduce the lock duration without increasing risk. You learned this on locomotives. Steam, timing, on a K4 Pacific. Same principle. The valve doesn't care how long it's open as long as it's fully open when steam enters and fully closed before the piston reverses. The timing window can be tighter than what the original designers specified if the system is well maintained and the inputs are consistent. Delacroix shook his head slowly. I've been teaching machine gunnery for 19 years. I thought I understood these weapons. An armourer from the railroad just explained something that every ordnance expert in the country says is impossible. The environmental testing was more challenging. They needed to prove the modification worked in conditions that replicated actual combat. Extreme cold, extreme heat, mud, sand, and salt water exposure. Camp Butner's facilities were limited, but Hartmann was resourceful. He requisitioned a walk-in freezer from the base quartermaster, claiming it was needed for cold weather equipment testing. He arranged access to the base swimming pool for water immersion tests. He obtained sand from the motor pool's storage yard and red clay mud from the engineering battalion's construction sites. On April 2nd, they subjected the modified gun to -20 degrees Fahrenheit for 6 hours, then fired 200 rounds immediately after removal from the freezer. The gun functioned normally. They submerged it in pool water for 30 minutes, then fired without cleaning. The gun functioned normally. They packed the mechanism with sand, cycled the action manually to clear the worst contamination, then fired. The gun experienced 2 stoppages in 100 rounds, both from sand in the feed mechanism rather than breech timing issues. The stoppage rate was actually better than standard M1919s showed in similar sand testing. The data accumulated. 5,000 rounds total, 7,000, 10,000. Each firing session was documented with temperature readings, round counts, stoppage records, and component measurements. The pattern was consistent and undeniable. The modified gun fired at 800 rounds per minute across all environmental conditions, with reliability that matched or exceeded standard M1919 specifications. By late April, Hartmann had compiled a technical report that filled 37 pages with test data, engineering analysis, and photographic documentation. The report was professionally formatted, complete with comparison tables showing performance metrics against standard weapons. It looked like something Springfield Armory might produce, because Hartmann understood that institutional credibility mattered as much as actual results. He also understood that sending this report through normal channels would ensure it disappeared into bureaucratic review processes that could take months or years. The 3rd Armoured Division was scheduled to ship to England in June, part of the massive build-up for the invasion of France that everyone knew was coming. If Kovalchik's modification was going to help anyone, it needed to reach combat units before the invasion, not after years of committee reviews. Hartmann made a decision that would either end his career or save it. He bypassed Ordnance Command entirely and sent the report directly to Major General Maurice Rose, Commanding General of the 3rd Armoured Division, with copies to Lieutenant General Jacob Devers, Commanding General of the Army Ground Forces. It was a breach of protocol that could result in relief from command. It was also the only way to ensure the report reached people with authority to act immediately. The response came faster than anyone expected. On May 9th, exactly 2 months after the initial demonstration, a convoy of vehicles arrived at Camp Butner, carrying representatives from Springfield Armory, Aberdeen Proving Ground, and Ordnance Command. Leading them was Colonel René Studler, chief of the Small Arms Branch at Springfield Armory, a man who'd spent 26 years in weapons development and held strong opinions about proper engineering procedures. Studler was furious. His opening statement in Hartmann's office made that clear. "Colonel, you have violated approximately 15 separate regulations governing weapons modification and testing. You've bypassed established review procedures. You've conducted unauthorized experiments using military property, and you've made claims about breech timing that contradict established engineering principles. I'm here to determine whether this entire situation represents incompetence, insubordination, or deliberate sabotage." Hartmann remained calm. "Colonel Studler, I'm here to show you a machine gun that fires 800 rounds per minute, with reliability equal to or better than standard M1919 specifications. You can spend the day listing regulations I've violated, or you can spend it examining data that could save American lives. Your choice. They went to the range. Studler brought 2 engineers from Springfield Armory, both of whom had worked on the failed high rate of fire development program that had consumed 18 months and produced no viable results. They approached the test stand with visible skepticism, bordering on contempt. Enlisted armorers did not solve engineering problems that defeated Springfield Armory's best designers. Kovalchik demonstrated the gun personally. He fired 500 rounds in controlled bursts, while Studler and the engineers watched with stopwatches, measured the cyclic rate, and examined the spent casings for pressure signs. The cyclic rate was exactly what the report claimed, 807 rounds per minute. The brass showed no excessive pressure, no case head separation, no signs of dangerous stress. One of the Springfield engineers, a civilian named Robert Morrison, who'd designed breech mechanisms for 15 years, asked to disassemble the gun. Kovalchik handed him the tools. Morrison worked methodically, removing the breech block, barrel extension, and recoil spring assembly. He measured the cam track with precision calipers, examined the locking lugs under magnification, checked headspace with gauge blocks. "The modifications are exactly what the report described," Morrison said to Studler. 0.04 inches removed from the cam track engagement surface. Locking lugs reshaped to reduce engagement depth by 0.02 inches. Spring tension adjusted to compensate. It's crude work, done with hand tools rather than precision machinery, but the principles are sound. "Principles we determined were unsafe," Studler countered. "We determined they were unsafe based on theoretical analysis of worst-case ammunition pressure variations," Morrison replied. "But Sergeant Kovalchik isn't using worst-case ammunition. He's using current military production cartridges that have pressure variations under 3%. With that consistency, the safety margins we built into the original design are excessive." "You're suggesting Browning over-engineered the breech timing?" "I'm suggesting Browning designed for 1919 ammunition quality. It's 1944. Manufacturing has improved dramatically. The design can be optimized for current conditions." The discussion continued for 3 hours. Engineers debated chamber pressure curves, breech unlocking forces, and factor of safety calculations. Studler remained skeptical, arguing that field conditions would introduce variables that laboratory testing couldn't predict. Morrison countered that 10,000 test rounds across multiple environmental conditions represented better validation than theoretical analysis. Finally, Studler made a proposal. "We'll conduct formal validation testing at Aberdeen Proving Ground. 50,000 rounds minimum, full environmental, stress protocols, complete metallurgical analysis. If the gun passes, we'll consider limited field trials with volunteer crews. If it fails, this entire project ends, and everyone involved faces appropriate disciplinary action." Hartman agreed immediately. It was the best outcome he could have hoped for: official recognition and formal testing, rather than courts-martial and career destruction. The Aberdeen testing began on May 23, 1944. Aberdeen Proving Ground in Maryland was the Army's primary facility for weapons evaluation, equipped with environmental chambers, high-speed cameras, and metallurgical laboratories that could analyze material stress at microscopic levels. The testing protocols were designed to replicate 10 years of combat use, compressed into 6 weeks of controlled abuse. Kovalchik's modified gun, now officially designated as Test Article M 1919E1, underwent punishment that no combat weapon would ever experience. It fired 10,000 rounds in a single day, with barrels changed every 1,500 rounds to prevent heat damage. It was frozen to -40 degrees Fahrenheit, then fired immediately. It was heated to 130 degrees, then fired immediately. It was submerged in salt water for 8 hours, removed without cleaning, and fired. The gun performed flawlessly. Stoppage rate across all conditions measured 2.8%, actually slightly better than the 3.2% that standard M 1919s averaged. The metallurgical analysis showed no stress cracking, no accelerated wear, no indication that the modified breech timing was causing structural damage. By June 27th, when the final test report was completed, Test Article M 1919E1 had fired 73,412 rounds without catastrophic failure. The report's conclusion was carefully worded but represented complete validation. Modifications to Breech. Timing and locking engagement demonstrate feasibility of increasing cyclic rate to 800 rounds per minute without compromising reliability or safety. Recommend limited field trials with combat units to validate performance under actual operational conditions. But by June 27, 1944, American forces were already in France. The D-Day invasion had occurred on June 6, 3 weeks before Aberdeen's testing concluded. 3rd Armored Division had landed at Omaha Beach on June 15 and was pushing inland through the Norman hedgerows. The careful bureaucratic process of validation, testing, and field trials had been overtaken by the brutal reality that soldiers needed better weapons immediately, not after months of cautious evaluation. Colonel Studler made a decision that bent regulations without quite breaking them. He authorized production of 500 modified M1919s under emergency procurement procedures that allowed field expedient solutions when circumstances justified bypassing normal approval channels. The guns were designated M1919A6, indicating they were the 6th approved variant of the basic design. They were shipped to European Theatre of Operations on July 8 aboard a Liberty ship carrying general ordnance supplies. The modified guns reached frontline units in mid-July, distributed initially to 3rd Armored Division since that unit's commander had personally endorsed the development. They arrived without fanfare, mixed in with regular replacement weapons and identified only by a small A6 marking stamped on the receiver. Most soldiers who received them didn't realize they were firing modified weapons. They just noticed that their machine guns sounded different and fired noticeably faster. Staff Sergeant Robert Hendricks of Company C, 33rd Armored Regiment, received M1919 A6 serial number 0047 on July 19 during a rest period near Saint-Lô. His original gun had been destroyed 2 days earlier when a Panzerfaust hit his Sherman tank, killing the driver and wounding the loader. Hendricks, who'd survived with shrapnel wounds and second-degree burns, was back with his unit after 3 days in a field hospital. The gun looked like every other M1919 he'd fired, maybe slightly cleaner since it was new from ordnance supply. He test-fired it that afternoon, burning through a 100-round belt to check function. The cyclic rate surprised him, faster than the gun he'd lost, noticeably so. He mentioned it to his gunner, Corporal James Martinez, who'd been firing Brownings since training at Fort Knox. "This thing's running hot," Martinez said. "Fires like somebody's holding the trigger down even when you're shooting bursts." They didn't complain. In hedgerow combat, where German infantry lurked behind every earthen wall and American tanks advanced through lanes barely wider than their tracks, any advantage in firepower mattered. The hedgerows turned every field into a potential ambush site. German Panzerfaust teams would wait until American armor was within 50 yards, fire from concealment, then disappear into the vegetation before American gunners could respond effectively. The modified gun's higher cyclic rate proved valuable immediately. On July 21, Hendricks's tank was advancing through a sunken lane when German infantry rose from a hedgerow 30 yards ahead. Martinez opened fire with the bow machine gun, while Hendricks traversed the turret to bring the main gun to bear. The German soldiers began falling before they could bring their Panzerfausts into position. Martinez fired a 5-second burst that put roughly 67 rounds into the hedgerow, compared to the 37 rounds a standard gun would have delivered in the same time. The difference between 67 rounds and 37 rounds was the difference between suppression and annihilation. German soldiers who might have survived to return fire or retreat were cut down before they could react. It wasn't sporting. It wasn't fair. It was the brutal mathematics of combat where fractions of seconds determined who lived and who died. Hendricks filed an after-action report that evening, noting the machine gun's performance without knowing why it performed differently. Bow gun demonstrated excellent suppressive effect against enemy infantry. Rate of fire superior to previous issue weapons. Recommend continued use. Similar reports began arriving from other units that had received the modified guns. The reports were brief. often just single sentences in the daily operational logs that company commanders maintained. But the pattern was consistent: higher rate of fire, better suppression, positive crew feedback. The modified guns were working in combat exactly as they'd worked in testing. By August, word had spread through informal channels that some M1919s were fast guns that fired noticeably quicker than standard issue. Soldiers began requesting them specifically, though supply officers couldn't always accommodate since only 500 had been produced and demand far exceeded availability. The guns acquired nicknames: zip guns, speed burners, 800s. The last term used by soldiers who'd somehow learned the actual cyclic rate. The official recognition came on September 4, 1944, when Ordnance Command issued Technical Bulletin ORD 9-44-31 authorizing general production of the M1919A6 modification. Springfield Armory retooled to incorporate Kovalchik's Breech modifications into standard production, using precision machinery to achieve the same dimensional changes he'd made with hand files. By October, A6 models were rolling off production lines at 800 units per week. The timing mattered. September and October of 1944 saw some of the heaviest combat of the European campaign as American forces pushed toward Germany through Belgium and into the Siegfried Line fortifications. Machine gun ammunition expenditure during this period averaged 3 times normal consumption rates, as infantry units fought through prepared defensive positions where German forces had entrenched for extended resistance. The A6 guns contributed to American tactical advantages that were difficult to quantify precisely, but showed up in casualty exchange ratios. American infantry units using A6 guns in defensive positions reported that German assault troops broke off attacks earlier and with less persistence than earlier in the campaign. The psychological impact of facing sustained fire density discouraged the kind of determined infantry attacks that had characterized German defensive tactics. Private First Class Donald Reuter of the 28th Infantry Division wrote home in October with observations that revealed the practical effect. Our machine gun sounds like a zipper when Jimmy fires it. The Krauts don't like pushing into that kind of fire. They'll probe once, maybe twice, then fall back and call for artillery instead of pressing attacks. Makes our job easier when they're scared of the sound. By war's end in May 1945, approximately 18,000 M1919, 6 machine guns had been produced and issued to combat units in Europe and the Pacific. The guns performed reliably across all theaters, accumulating combat records that validated what Kovalchik had demonstrated in his illegal experiments at Camp Butner. The statistical analysis was conducted after the war by the Historical Section of the Army Ground Forces, examining after-action reports and maintenance logs from units using A6 guns versus units using standard M1919s. The data showed that A6 guns achieved 23% higher suppressive effectiveness in measured engagements, required 14% less ammunition expenditure to achieve equivalent fire density, and recorded stoppage rates that were actually slightly lower than standard guns, despite their higher cyclic rate. That last finding surprised ordnance analysts who'd expected faster cycling to increase wear and failure rates. The explanation lay in understanding that the A6 modifications reduced breech battering by optimizing timing. The breech locked more efficiently and unlocked more smoothly, reducing the mechanical violence that caused accelerated component wear in standard guns pushed to their operational limits. Michael Kovalchik never fired a shot in combat. He remained at Camp Butner throughout the war, training armorers and maintaining the division's weapons after 3rd Armored shipped overseas. His role in developing the A6 modification was documented in official records but not publicized. The Army preferred to credit Springfield Armory with the development, avoiding the embarrassing admission that an A66 modifier, enlisted armorer, had solved a problem that defeated the institution's best engineers. Kovalchik was promoted to technical sergeant in November 1944 and received the Legion of Merit in February 1945 with a citation that noted his exceptionally meritorious service in the development and testing of improved automatic weapons systems. The citation didn't mention that his work had been unauthorized or that he'd violated regulations. Those details were quietly buried in classified sections of after-action reports that wouldn't be declassified for decades. After the war, Kovalchik returned to Pittsburgh and went back to work for Pennsylvania Railroad. He spent 26 years maintaining locomotives, retiring in 1971 as a master mechanic. He rarely discussed his wartime service, and when he did, he focused on the mundane details of armory maintenance rather than the modification that had increased combat effectiveness for thousands of soldiers. In a 1987 interview with a military historian researching small arms development, Kovalchik was asked if he felt proud of his contribution to the war effort. His answer revealed the perspective of someone who'd understood that engineering served human purposes rather than institutional validation. "I didn't think about contribution or pride," he said. "I thought about soldiers who were getting killed because their guns fired too slowly. I knew how to make the guns fire faster, so I did. That's all it was. You see a problem, you have the skills to fix it. You fix it. Anything else would have been cowardice." The interviewer asked if he'd been scared of courts-martial when he began his unauthorized modifications. "Terrified," Kovalchik admitted. "But I was more terrified of reading casualty reports and knowing I could have prevented some of those deaths if I'd been willing to risk my career. The army could take my rank, throw me in prison, dishonorably, discharge me. They couldn't make me live with knowing I'd chosen safety over doing what was right." Lieutenant Colonel Hartman's career survived the breach of protocol that had brought Kovalchik's work to official attention. He was promoted to full colonel in October 1944 and commanded an ordnance battalion supporting Third Army through the final months of the European campaign. After the war, he testified before a War Department board, reviewing weapons development procedures, arguing that institutional conservatism had nearly prevented a valuable innovation from reaching troops who needed it. His testimony contributed to post-war reforms that created more flexible procedures for field expedient modifications and faster review channels for soldier-initiated improvements. The reforms acknowledged what Kovalchik's story had demonstrated, that valuable innovation could come from unexpected sources, that institutional expertise didn't monopolize good ideas, and that regulations designed to prevent failure could also prevent success. The M1919A6 remained in U.S. military service until the 1950s, when it was gradually replaced by the M60 machine gun, a completely new design that used gas operation but incorporated many of the lessons learned from wartime experience. Ironically, the M60's designers faced similar challenges with cyclic rate optimization and breech timing, and they consulted Kovalchik's test data when developing their own solutions. Some A6 guns saw combat in Korea, where their higher rate of fire proved valuable in the same ways it had in Europe, providing suppressive fire density that helped American infantry maintain tactical advantage against numerically superior Chinese forces. The guns performed reliably in Korean winter conditions that matched the environmental extremes they'd been tested under at Aberdeen Proving Ground. The technical legacy of Kovalchik's work extended beyond the specific modifications he'd made. His approach demonstrated that optimizing existing designs could sometimes achieve better results than developing completely new weapons, that manufacturing improvements changed the parameters of what was mechanically possible, and that conservative safety margins, designed for one era's technology, might be excessive when applied to improved manufacturing standards. Modern firearms designers study the A6 development as a case study in lateral thinking and practical engineering. The story is taught at Army Ordnance schools as an example of how field experience and non-traditional expertise can complement institutional knowledge. Kovalchik's willingness to question established doctrine without formal credentials became a model for encouraging innovation from soldiers at all ranks, rather than restricting development to specialized engineering organizations. In 2003, 60 years after Kovalchik began his illegal experiments, the Army Ordnance Corps inducted him posthumously into the Ordnance Hall of Fame, recognizing his contribution to weapons development. The citation noted that his modifications had significantly enhanced combat effectiveness of the M1919 machine gun and demonstrated the value of field expedient innovation in meeting urgent operational requirements. Kovalchik had died in 1996 at age 78, Never seeking recognition for work he considered merely doing his job, his children discovered his wartime notebooks after his death, careful records of measurements and test results that documented how a railroad mechanic had solved a problem that defeated ordnance engineers with decades of formal training. The notebooks are now preserved in the Springfield Armory National Historic Site, displayed alongside examples of the M1919A6 and technical reports documenting its development. Visitors who examine the notebooks see hand-drawn diagrams, precisely recorded, measurements and calculations that reveal methodical thinking rather than lucky guessing. The work of someone who understood mechanical principles deeply enough to apply them across different domains. The broader lesson wasn't about machine guns or breech modifications. It was about the relationship between expertise and innovation, between institutional knowledge and individual initiative. The ordnance establishment had possessed all the technical resources necessary to develop the A6 modification. They had precision machinery, metallurgical laboratories, trained engineers, and comprehensive test facilities. What they lacked was the willingness to question fundamental assumptions about what Browning's design could and couldn't do. Kovalchik had none of those institutional resources. He had a file, calipers, a reject gun nobody would miss if he destroyed it, and the confidence that came from understanding that mechanical principles didn't respect credentials. He'd learned on locomotives that timing could be optimized when system inputs became more consistent. He'd applied that lesson to machine guns because the mechanical logic was identical even though the applications were different. The Army's initial resistance to his work wasn't stupidity or obstinacy. It was institutional caution developed through decades of experience with catastrophic failures that occurred when people modified weapons without understanding the complex interactions between components. That caution served valuable purposes, preventing dangerous experimentation that could kill soldiers. But it also created barriers to beneficial innovation that came from outside approved channels. The resolution wasn't to abandon institutional caution or to encourage unlimited freelance modification. It was to create systems that could distinguish between dangerous tinkering and valuable innovation, that could evaluate ideas based on data rather than credentials, and that could move faster than bureaucratic review when circumstances demanded urgency. 18,000 M1919A, 6 machine guns firing 800 rounds per minute instead of 450, 37% increase in fire density, 23% improvement in suppressive effectiveness, 14% reduction in ammunition consumption. Numbers that translated into tactical advantages that saved American lives in hedgerows, forests, and urban combat from Normandy to the Rhine. Behind those numbers stood a sergeant who'd risked courts-martial because he believed doing nothing was a greater moral failure than breaking regulations. A lieutenant colonel who'd risked his career to bypass institutional barriers because he believed combat effectiveness mattered more than bureaucratic procedure. And engineers who'd been willing to admit that their theoretical analysis had been wrong when confronted with empirical evidence that contradicted their conclusions. The story of the M1919. A 6 is the story of how innovation happens when institutions allow it, how expertise from unexpected sources can solve problems that defeat conventional wisdom, and how individual initiative, guided by competence and moral courage, can change outcomes when systems are flexible enough to listen. Michael Kovalchik filed an illegal breech modification that made 30 caliber machine guns fire 800 rounds per minute instead of 500. He did it because soldiers were dying, and he knew how to help them. That choice, made in a quiet armory shop during night shifts, rippled through combat zones across 2 continents and altered the tactical calculus of infantry combat in ways that saved lives and ended threats. The impossible, once again, proved to be merely the unexplored boundary of what competent people were willing to attempt when the cost of inaction exceeded the cost of risk. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.